So graph is currently one of the largest research topics in AI MLs in recent years, and there are certain reasons for that. One is that graphs are very pervasive in many scientific disciplines. The second reason is that now we have models to deal with vectors, sequence, grid, and other regular structures, but we still don't have the model to deal with irregular structures with random connectivities. So it's time to move on to that, the new space. So one of the space is called set. Set is the group of elements that doesn't have any orders. And graph is another one. Actually, set is special case of graph where we don't have any connectivity between the elements. And graph is a generalizations where we have nodes and have the connectivity between nodes. Graph are very difficult because we don't have regularities in structures. We have the different size, and we don't have the precise orders, and we don't have the regularities in connectivities. So here is an example of how graph may plays a role in system medicines. At the lower levels, we have the interaction between molecules, like between protein and proteins, and those define the basics biofunction in our bodies. At the higher levels, we may have the interaction between the cells, like cells sending the signals to communicate between them. So our brain is actually one of the largest cells network available with about 100 billion cells and communicating with each other. And we have something like 100 trillions of communication between channels, communication between the cells. Moving up to the higher level, we have the system of organs and tissues. And those systems work together in harmony to define our living bodies. So modeling of this kind is still the dream of system medicines, but this gives you an idea that how the graph may play the roles in these complex topics. So here are more details of how the graph plays the roles in biologies and chemistries. So here the molecules are represented as the graphs, where we have atoms as a node in the graph, and the bonding between atoms are edges. So from this graph, we can learn a model to compute the molecular properties of the graph, like what is the energy function, or what are the biological and chemical properties of that. We can also predict the interaction between the two molecules by formulating the graph and graph interaction problems. When we can also predict the productive reactions, where we can model the set of molecule as a complex of graphs, and the changing between bondings are actually the result of the reactions can be modeled as a dynamics of the graph. I will touch some of those topics later. In material science, a graph can be used to represent crystal structures. So crystal is a special structure that are repeated over space in a material. So using a graph, in the same way that we model the molecules, we can represent structures of the crystals and compute the property of the crystals. More importantly, we can use the graph to have design the new materials that may have the certain property that we want, that certain chemicals or physical properties like hardness and boiling temperatures and conductivities and things like that. It's very exciting space that, and we've seen the graph networks playing the important role in the recent years. In videos, in the past, video is traditionally a sequence of frames, And in theory, we can use CNN to model the frame or set of frames, depending on we want to model 2D, 3Ds. But we could use the graph to model the videos in a more systematic way, so that we can extract objects, localize actions, and model interaction between objects throughout the space and time, and model this entire entity, action, and evolution of system over time as a spatial temporal graphs. So given that we could do, what are actually the graph neural network is doing? So let's start from the a graph of between entities on the top left corner. So one way to do that is to define a way to communicate between the entity in the graphs. Um, Here's one example of the rules. We have the rules called ZCN rule, and ZCN stand for the graph convolutional networks, which is extension of the standard CZN to the arbitrary connectivity structures. So this has the idea that we can refine a state of a particular node based on the state of the neighborhood node, subject to some linear transformation and normalizations. We can abstracting out those update rules by using the matrix formula. And that is a special case of the more generic mechanism called message passings. So the idea is that a state of a node can update itself based on the message sending from the other nodes. And the neighborhood is defined by the structure of the graph. By collecting all the messages sending from the neighborhood, the current node can combine the message with its own state, and using the certain linear combinations and nonlinear transformations to refine its states. And in this turn, in return, it also send other message to the neighborhood, and that neighborhood can update its own states. And that loop can keep repeated for all the nodes in parallel until um, we reach certain conversions. For example, the state of the network cannot change with more message passings. And the message passing is very simple and powerful mechanisms, even though it's local in for each steps. But with many steps, it reaches global properties. One of the main properties that creates some sort of consistency between the nodes. And the implementation of each node now incorporate all information from the neighborhood, not just the direct neighborhood, but indirect neighborhoods. So that at the end, we can do labeling of this node if the task is for the node labeling. But if the task is the graph labeling, then we can do the poolings of all of those states and put through a feed-forward network to predict the labels. So there are options in the updating rules. So we can keep the parameter sharing between the step of updates, and that we have the recurrent networks. And if the connectivities of between the node are regular and repeated over time, we have actually we have the CNN. And if skip connection are used between the steps, we have the rest nets. So that's to say that CNN rest nets are all special case of the graph message passing mechanism in the graph neural networks. So we have an option to decide which message sent from the neighborhood to be more important to the other. So that mechanism is called the attentions. And optionally, we can have a multiple attention heads to define multiple weights for different at the same time. So that's create a sort of self-normalized message passing mechanisms. So in the ZCN, the normalization is done by the structure of the networks, and there's no learning in the in the attention probabilities, but we can add the learning in the attention probabilities in. So as a result, we have the attention graph that was introduced a couple of years ago. So message passing give us an update of the state of the each node of the graphs and create some sort of consistency, cell consistency among the nodes. But then when the graph itself change the connectivities, then that message passing have limited powers because now the connectivities have changed. Then messages cannot be sent like before anymore, and it cannot predict what edge to be changed, whether we have the new edge or we have the remove the old edge, or we change the nature of the edge, right? So that's the problem of the what we call graph morphisms. And the graph morphism is setting where we have the nodes, the set of node doesn't change, but the set of edge change, right? And since the chain of theirs are discrete, the message passings have a limited power to do so. Okay. So here's one example of one of solutions introduced by Kian Do and his colleagues. And the model was called graph transformations policy networks. So the idea is that we consider the chains of the graph sequentially, one S at a time. And because it's to change the discrete, so we can apply policy gradient techniques in reinforcement learning to compute the um, likelihood of the sequence of chains and learn from there. Okay? So here the graph neural network is still being used to update the state of the nodes whenever we have the chains. And then from that node, from that update, we can predict what the next change is and keep repeating from predicting and updating until we're satisfied with the entire sequence of chains. So this one was applied for chemical reaction problems where the set of atom doesn't change, but the bonding between the atoms change in the reaction process. Another problem, more difficult problem, is that what if the structure of the graph itself changes over time? And what if there are many chains happening in a sequence? And that's very interesting because it happened. We can see that happen in the real world. So we have the change in the node implementation and change in the connectivity of the network itself. So for examples, in our daily communication networks, so each day we may send email to a couple of recipients, and that recipient can be old or new recipients. But each day the connectivities in our personal networks may be entirely different from the previous days. Then that creates a very interesting dynamics that need to be modeled properly. So there are a couple of ways to deal with that. If the set of node doesn't change so much, we can maintain one recurrent network for each node just to model the temporal dynamics. And within each time step, we can use the standard message passing mechanism to update the node within the time steps. But if the node itself changes, and if everything time step have a different set of nodes, and there's no direct corresponding between the two, between the set of nodes, then we can still learn to model the dynamics of those chains by using another model, it's called hypernetworks, that learn the parameters and the nature of the message passing between the nodes, regardless of the node IDs. So that can be done through the hypernetworks that we reviewed before, and that enables us to model very flexible dynamics of the graph. Then here's an example of a special dynamics called asynchronous and sparse interactions. So in these settings, we have a set of entities, then the interactions could be very sparse, just like our email networks. And in this setting, we assume that there are the state of the objects may not change that frequent until something happens. So let's say we have the system of multiple human and multiple objects interacting in a complex ways in the videos. So we know from the physics that for objects, it doesn't change its state of motions unless some force acts on it. Like for example, if it sit there, it keeps sitting there unless someone touch it, or if it drop, it keep dropping unless something's or unless it hits the floor, right? But for human, it's more complex because human have certain plan in mind. Let's say um we cook breakfast and we have certain recipes and we have certain way to handle um the ingredients and the cooking methods. Then our interaction with the objects within the kitchen could be very complex and unpredictable, right? But the overall thing is that our interactions could be sparse because whenever we need to touch something, the state of um, that object may change. But if you don't touch, the state of that object doesn't change. So the touching is also both sparse and asynchronous, and that requires to create a special kind of networks that um, handle the asynchronicities and sparsities in the networks. So in this model, um, the we created a special kind of recurrent networks where we have two layers. The lower layers are frequently updating a state and make decision whether we change something. And the upper layers called segment layers when it's only change its label if the hard decision has been made. So the segment layer is very sparse, but the frame layers or the lower layers could be regulars. This combination is powerful because we can do both segmentations of activities and labeling activity at the same time. This has been shown to work very well um, in modeling the video, suggesting that it's important to respect the nature of the data. That in this case is that the state changes infrequently, and the communication between the entities is sparse. And second is that it says the graph neural networks are actually very powerful techniques to handle this kind of complexity. The next important topics of graph neural networks is graph generations. So the goal here is to learn to generate arbitrary graphs from nowhere. Right? It's so difficult is because the graph doesn't have any regular structures to stick to. Like unlike sequence, you can do step by steps. Unlike grid, you can do either do the block by blocks or have to impose the prior structure in there. The graphs are also permutation invariant, so that we don't know what orders meaning what, right? And then the probability of generating a graph is not easy to model because unlike the sequence, we can use the chain rules in probabilities to compute the exact likelihood of a sequence. But the graph is not that easy. Of course, we can still define certain ordering to compute the likelihood using the chain rules, but defining the order itself is open research problems. And also because the graph has a variable in size, so we need to define what is the when to stop when you do generations, right? And also for a graph generation, especially in the field of chemistries, it's very important to aim for diversity of the graph generation because chances are we can generate a lot of graphs that look similar, and it's not very useful in discovery exercise in drug discoveries and chemical explorations. So there are some generation methods available in the literatures. The classic one in the 1980s is called random graph models, where we make assumption about the distribution of the connectivities and the distribution of the entire graph. But it was very hard to make a control generation in the graph. More reason we have a few options associated with generative models. And with the variational autoencoders, we have the graph VAEs, and we have GAN variant as well. The main difficulty of this is that although we now have very good generative models within neural network as main components, but graph is way more difficult because we don't have the fixed structure in mind, right? So exploring both structure and parameter at the same time is way more difficult than just generating a set of the image of vectors. So a more practical technique is using sequential methods and reinforcement learning algorithms to generate one element of the graph at a time. So we can think about the graph transformation networks that we mentioned before, where we generate one S chain at a time, and now we generate one blocks of the graph at a time, or delete one graph block at a time, until some criteria are satisfied. Here's an example of the recurrent networks that are designed for the graph generations. And here recurrent is maintained in the process of adding one node and one set of one S at a time. And here's another example of sequential models to generate one set of node at a time using reinforcement learning. So far, we have covered the structures and models of neural networks that's been shown to work very well, and some of them become the hot topic of today, including the transformer and graph neural networks. But we haven't touched the question how to learn those models yet. So most of the work so far have been based on supervised learning, where we have the training signal, and then from there we can estimate either model structures or the model parameters. However, when the labels are not available, external labels are not available, we need to turn into the unsupervised learnings, and that is a topic of the next part of to talk. So before we go into technical detail of how unsupervised learning happens and how neural networks can be easily trained with unsupervised learning techniques, let us start from the basic concept of representations. A representation is the use of psi that stand in or take the place of something else. So it means that we can use something to replace something else for a certain purpose. And that's something else, the replacement itself is representations. And learning to do so is called representation learning. And representation learning has been a main game of neural networks in the early days, in the 1980s. And its interest has returned in the current world of deep learning, starting from 2005, 2006, until now. The main goal is that we want to replace the feature engineering, a manual feature engineering that was popular in the 1990s and 2000s, by an automatic way to extract information from the raw data so that it represent the data better, and it make the predictions easier. Right? So as a result, between 2006 and 2012, there are many unsupervised learning models that's come from the neural networks literatures. So we have the restricted Bose machine, we have the deep binary networks, we have deep Bose machine, we have denoising autocoders, deep denoising autocoders, and other sparse methods. However, between 2013 up to 2018, since the AlexNet, most of the neural network was supervised. This was because we couldn't have any, we didn't have the similar performance when using unsupervised learnings. And Alex Let was a defining moment that now we can just collect a lot of labels and we have very powerful method for downstream task. And that's for the past for the period of like a 7 or 8 years, the entire field was like that. However, since 2018, the major progress has been happening in unsupervised learning with neural networks. And now, in certain aspect, we have very competitive result with the new um, techniques that's happening. So in NLP, we have BERT, and in other fields, we have contrasted learning and self-supervised learnings. And now, the new chapters of unsupervised learning has opened. Before we go there, let's us quickly review what's available in the literatures. So starting from the early day, you have the autoencoders. So autoencoder is a very simple mechanism so that we want to map the data into the latent variables and using that latent variable to reconstruct the data itself. So the latent variables act as the bottlenecks of the reconstruction because normally the dimension of the latent variable is smaller than the dimension data. So that's only few bits, the only important part of information is it kept, and therefore reconstruction is normally less noisy. So that is the deterministic versions. So the probabilistic version of the autoencoder is called the restricted Boson machines. Here we have two layers, but they are stochastics, so that learning happens to find agreement between the hidden layer and the input layers. Autoencoder have a linear cousins called PCA. So um, PCA actually do the same thing. It projects the data into the latent space and then project it back to recover the original um, signals. Um, from Boson, from restricted Boson machines, we can stack multiple layers into the deep models. And now we have a version called deep belief networks. And that was 2006, and that was a defining moment for the modern deep learning's revolutions. To be able to introduce certain stochasticities into the encoders, we have now denoising autoencoders. So denoising autoencoder works by introducing a small noise to the inputs, and we ask the model to reconstruct, to denoise the model to recover the original data. Adding the noise make the model to focus on the more important parts and ignoring the noise. And as a result, we have a way to learn quite more robust representations. So, and that was for the vector structures. And now adding the convolution to the mix to represent image, we have the thing called the deep convolution inverse graphics networks. So what it means is that we have the encoders and have decoders, and encoders, the decoder part is called the encoder part is called the inverse graphics, and decoder part is equivalent to graphics in computer visions, in image processing. Now, so we have a plenty of unsupervised models right now. So what are the criteria for a successful implementation learnings? So there are a couple of criteria. One is that a good implementation should learn to separate out the factor variations. And in the modern term, it's called disentanglements. The factor variations are useful when they represent kind of independent factors that control the generation of the data. Like for examples, a picture of the face, we have a couple of factor variations like the pose, the lightings, and the occlusions, like wearing glasses and scarf. But that's it's a bit too much to ask for a unsupervised learning model to separate those factors out because the infinite number of factor combination that's equally good to in generating the same data. So it might be better to ask whether the factors are linearly correlated with the task that we are interested in. So that might be easier to 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 get rather than asking for the true independent between the factors. A important aspect of a good implementation is that it should give us some abstraction data that are invariants against certain variations like deformation or noise. Another one, another characteristic of a good implementation is that it's somehow distributed in the sense that um, a concept is represented by multiple units at the same time. At the same time, should be compact for storage and post processings. And if so compact, and it's offer a way to do the dimensionality reductions, right? From time to time, it can be sparse if you want to really encode certain symbolic structures. So those are a few criteria for designing a model to learn a good implementations. So the question is that, given those criteria, why should we use neural networks for the task? We have before a lot of unsupervised learning techniques like PCA, ICA, HMM, and other things. Right? They can be trained without any labels. But why should we use neural network for the task? There's some reason for that. One is that neural networks have very good implementations power, right? So we know that feed-forward network could be universal function approximator. It means that we can, for any function that exists, we can find a neural network that arbitrarily approximate the functions. The RNN is even more powerful. In theory, it can approximate any programs that we can think of. The CNN is very powerful for capturing any data that repeated pattern over time and space. And transformer, as of now, is very powerful contextual encoders that encodes the long context and represent data so that it have long-term dependency. Another important aspect is that neural networks are normally compact. Normally, as I mentioned before, the representation of neural network can be sparse and distributed at the same times, and very easy to process and um, in the later part and store. Right. Neural networks in recent years have certain ability to account for uncertainties. We can actually introduce stochasticity into the models and estimate the distribution of that. One aspect less successful so far for neural network is the symbolic representations, because we believe this, symbols are important for certain high-level cognition functions. However, we can still be able to represent the symbolics symbols by using sparse activation and gating mechanisms or attentions. So those are still open for research. But given those properties, it suggests that neural networks could be a good candidate to implement unsupervised learning. So one of the very successful idea is called the neural autoregressive models. So it's now seen in many forms, like for example, the language models that we've seen in the extreme case of GPT-3. So that the idea is very simple. We can use the same mechanism, same set of parameters to learn a model so that it predicts the next input, next data point, given the previous data point, right? Doing so gives us a way to model the long-term dependencies and also model the orderings, and with parameter sharing, we have the complex models. And neural networks are easy to share parameters and easy to implement those ideas. The idea actually is very generic, and it can be implemented to many ways. The RNN is a classic one, but you can use CNN as well. Like we can use one-sided CNN, dilated CNNs. So the powerful examples wavenet, so we can have it to generate musics. For image, we can have the pixel CNN. So we can generate one pixel at a time in a certain order. So if we have the transformer as a backbone, we can have the GPT-3, GPT family, right? So if we use the autoencoder as a backbone, we have the thing called mate. Right? The good thing about auto regressive model is that it normally generates a good quality data. The main problem is that it's very slow because you have to take one step at a time. Right? So as a result, we need, if you want to scale better, we need to design a special way to handle to introduce inductive bias for scalability, and that's still an open research problems. Another way to achieve unsupervised learning is to the generative models. So that the main principle behind this thing is that we learn certain underlying mechanisms behind the data, right? So in terms of statistics, we learn a distribution of the data so that it fits the real data well. Modeling these kind of generative models have many applications because we can control the generations. We can, for example, we can generate speaks from text. We can simulate the data that's really hard to acquire or share, like for example in healthcare or in certain security applications. So we can do other things. We can do semi-supervised learnings because we can introduce the data distribution into the mix, and using generative models, we can do planning. One techniques become standard and in the like 5 years ago, and still using these days is called autoencoders, as I mentioned before. So the idea is very simple. It's learned to reconstruct itself by coding the data in a certain form and decoding that form into the original form. It's very ideas, and we can stack many layers into the deep models and introduce a noise into the input to make the model more robust. A probabilistic version of the autoencoder is called variation autoencoder. So the idea that we make assumption that there's certain simple distributions in the prior, it's hidden, and by varying the hidden variable, we can generate the data in the space that we are observing. The difficulty of that is that the inference is not easy because when we compute the hidden, we have to integrate out the data, and we compute the data, we have to integrate out the hidden variables. And integration is not easy if we have the complex distributions. So variance encoders introduce approximation tricks to that, so that instead of computing the posteriors of the hidden given data directly, we learn a network to approximate that posterior. So as a result, we have the two networks. One is encoders, and another one decoders. The encoder is also called the recognition networks, and the decoder is also called the generation networks. So as a net result, instead of learning to maximize the likelihood of data, we maximize the lower bounds of likelihood of data. VAE has seen then VAE has found a lot of application, and now it's one of the major ideas being introduced in the last 5 or 6 years or so. Almost parallel to VAE, we have another is called the GANs. It stands for the Generative Adversarial Networks. So unlike the VAE, which tried to optimize the data likelihood, GAN operated in a different way. It tried to match data statistics of a real data and the fake data. Right? It's not matching the data itself, but matching the data statistics. Right? So it has been considered one of the best ideas in the last 10 years by Zhang Likun. So instead of learning distributions, it create another two model. One is for genetic data, and another one is for the discriminating between the fake and the true data. And that factorization make the model interesting and at the same time it's more difficult, because at the end of the day we need to learn a minimax optimization problems where we have to learn a generator models that makes data similar to the simulate data similar to real data, and we learn the discriminator that try to distinguish between the two. So the process finishes when the discriminator cannot make any you cannot tell the difference between the two. Then here is a visualization of the process. So in the beginning we have the data that's generated from the models are so different from the real data, and the discriminator would easily to see the gap between the two. But when learning happens, the two distributions merge, and the discriminator have no way to make the distinguish between the two, and that when the learning process stops. Since then, there has been a lot of progress in improving GAN, because GAN in theory was powerful, but the actual learnings were difficult and unstable. But with the tricks of certain scalings and progressive trainings, we now have very successful GAN in many domains, especially in image, partly because image is easy to visualize. Then here's some few examples that I did 3 years ago. It looks so realistic to the point that for many faces, we cannot tell whether it's a real person or not. In fact, those are all fake generated um, images. Even though, yeah, that's another unintended consequence of this is that people exploit the technologies, and now we have the fake thing that generated from the machine. Probably most of the time it's from GAN. We have the fake images, we have fake videos, and probably we can have fake news as well. So that is the unintended consequence of some successful technologies, powerful and successful technologies. Now I'm moving to the one of the latest hot thing in the field. It's called BERT, and BERT is actually nothing but a transformer that learn to predict its own path using the other path. So learning to predict one part from the other part has been there for many decades, known as the pseudo likelihood estimations. And I remember it was introduced in the middle of 1970s, roughly like 40 something years ago, 45 years ago. But pseudo likelihoods was not easy to recognize because it was slow. If we learn to predict one token at a time. So BERT have a very nice way to overcome that difficulties by randomly masking some part of data and try to reconstruct that mask, right? So it doesn't satisfy the condition of pseudo likelihood anymore, but resolve that we can learn unsupervised learning, learn unsupervised surveillance, the data in parallels. So that very interesting ideas that works, and the key behind the success is actually a transformer, so that it encodes the long-term dependencies between the end tokens. Another idea that has been catching attention in this in the last year is called in the last 2 years, the contrastive learnings. So instead of learning to predict the part of data itself, or learning to generate the fake data that can be matched against the original data. So contrastive learning is based on the comparison between examples. For a particular image, for example, it search for a similar image and dissimilar image, and creating a loss that's separating out the dissimilar example from the similar example. Right? The principle is very simple, but it turned out to be very, very powerful when especially when combined with a way um, to generate dissimilar and similar image using the, augmentation techniques. And in image so far, uh, we have been able to find that application of contrastive learning that it's so powerful that it's almost match the accuracies of the supervised learning. The result it's very significant because for long time we couldn't have that matching performance between unsupervised learning and supervised learning, and now we have that, and I believe that's gonna be another defining moment for machine learning in general and deep neural network in particular. So before we conclude, there are a few more points that worth mentioning here. Um, why unsupervised learning is important? That's because one is that labels are expensive to acquire in many domains. And second is that label are actually offering only very few bits per labels. Whereas if we do unsupervised learnings, every single data point, data element in the data offers some bit of trainings. So that we may, for an image, we have a couple of thousand bits per image. And that's far more than only a few bits per labels, external labels. And we have those bits for free, right? There's some techniques that we didn't especially reviews or mentions, but there's some principle behind those unsupervised learning techniques. One is compressing data so that we can reconstruct data and maintain certain regularity in data, just like in autoencoders type of model. For many model, we can reformulate an algorithm as a energy-based model, where we learn the model so that the energies of the observed data is small, and energies of the data that are not observed are big. Right? So it can be seen in many models, including contrastive learning. A technique that's found to be powerful in recent years is called the self-supervised learnings. And it's very simple. It's to try to fill in the missing slot in the data. We could pick any element as a missing slot and try to fill it in. And then based on the basic idea that the data, rich data, are highly correlated and highly compressible so that any missing piece can be reconstructed from other elements that are not missing. So far, I have not covered the unsupervised learning of the graphs, but there are many options out there. But then, like for example, DeepWalks or GPT-ZNN, the latest one, which combine the graph neural networks and GPT. But the principles, those principles we have mentioned still holds. The only things that we have to deal with the irregular structure of the data. So that, and most of the time we apply certain message passing mechanisms to work with the unsupervised learning tricks. So one of the fundamental question is that are we for unsupervised learnings, are we what objective are we optimizing here? Is that likelihood, or is this reconstruction error? Is that or the free energies or anything, or no real objectives, right? So another more important question, and also important question, equally important question, is that if we have many interacting elements, can we expect certain emergence that coming out from those interactions in the unsupervised learning manner? There's no hint or no external neighbors for that emergence. But we've seen that in the real world, certain thing emerge from simple interaction as if there's something happening there, even though there's no real objective function to optimize. Right, so that is the end of part one, which I consider to be the deep learning version one, where neural networks plays a role for supervised learning, unsupervised learnings, and it can I have reviewed the major thing that show that neural can be made to handle variety of structures like vectors, sequence, grid, or graphs, and it could be done. Um, and it have reached certain maturities, so that most of the applied domain right now, whenever we have data, we can apply the supervised learning techniques with the model that we have developed so far, including the latest one like transformer or graph neural networks. But when we don't have data, we still be able to make use of unsupervised techniques that combine with um, unsupervised techniques that combine with the strong inductive bias give us for free in neural networks. However, one thing is still there and has not changed is that we still relies on gradient descent techniques to optimize some certain techniques, right? Um, and whether or not this is enough for AI, whether or not it's a way to move forward, we don't know yet, right? So that's the certain direction for the future that may define the next phase of deep learning are already there, and there are many people working on that, but they are not mainstream yet. And that is those are the topics of the next talk of the next part of these talks.